on top of it to do like checks and stuff like that. But on the CPU end, we also expose our C functions through a CAPI or C API, and that is done through these like command handlers. So when we say like we call a CAPI from our client, what it's actually doing is it's using our client DLL, our client library, to send a CAPI command over TCP to our MCFI server, and then we have threads workers that basically intercept that and then map it to the correct CAPI function and then return the results and stuff like that. And Chuck, please feel free to correct me at any point if there's anything that I say that's like incorrect. But now onto the more free space connector specific things. I've tried to separate out most of the free space connector stuff into like its own modules. Some of the more notable ones are this FSOC image module, which is basically just a data structure for our images, and it's just the baseline, the most basic unit is this FSOC image class, which is a dynamically allocated image container. And this was implemented a while ago, and I haven't touched it in a really, really long time.
Okay.
There's also this other stack, the FSOC image stack, which is, as it suggests, basically a stack of the images. And the way that this is used in our system is that we have a dedicated thread that all it does, a dedicated CPU thread, all it does is, sorry, let me take a step back. So the way that our image acquisition is set up currently, since our data comes from our FEMC and then to the ODC, and then the ODC transfers it to our GPU memory, and then it's read from the GPU. It's read from the GPU memory.
Here's the image of the.
Right. Yeah. So the image is copied into our CPU memory on our GPU schedule as well. So that's actually the only part of the CUDA schedule that got modified, which is just adding additional data transfer for this specific image data. And there is a dedicated CPU thread. All it does is it demuxes, so it turns the image data that is written from the GPU, which is in the form of a byte string, so it's completely flattened. There's some special demuxing technique that needs to be deployed because it's a 10-bit image, and the bits are very like arranged in a very interesting pattern. But there's that CPU thread. All it does is that it takes the most recent image in the dedicated CPU memory, and then writes it into an FSOC image, or one of these data structures, and then which is in one of these stacks. And then the stack is also deployed as like a rotating buffer, where I forgot the current allocated amount. Maybe it's like 50 images or something that we keep in memory, where it fills up this buffer, and then when we have to add a new image, it will replace the oldest image currently in this buffer. So we always have the most recent 50 or however many images available in memory. That enables a couple things. I don't think it's like super necessary to always maintain this many images, but if you want like a continuous stream, that can be utilized and also if you wanted to like potentially average the images across a number of acquisitions, in order to get a more stable image without as much image noise, you can use this image stack. So that's how the image setup works. And then that image stack is just, I believe it's implemented as a part of the contour singleton. So most CAPI functions would have access to that. And then there's also a where is
I've got. Don't sit down. No.
where is it?
I was going away anyhow. So, yeah, I will make you. Thank you very much.
Ooh.
Maybe I should make copies of there. Well, I'll make them one. It's kind of one at a time. Anyhow.
All right, there it is.
One will do.
Yeah. So onto kind of like almost like a custom image processing library that we had to write for this, and it's nested under Contour Math, and it's called CPU FSOC image processing, which I just have basically all of our image processing functions in here. It is implemented as a singleton, and the way that you would use this, some of the key functions in this library are, for example, if you want to do a correlation, like say you have your reference image, you have your reference image of what the ferrule or the end face looks like, and you want to find it in the current target image, there's a function for this. And then there's also functions for obtaining the focus value of a given image. So what it will do from a high level, what it will do is it'll run a correlation in order to find like the general region where you want to like look for your end face and evaluate your end face focus at, and then run your focus algorithm, which in this case is Brenner's gradient, as we've talked about before. There are also a couple of other functions in here that were like more just like your memory copy functions. Another one thing about like why it's implemented as a singleton is because there's a lot of statically allocated memory for image processing. So we have our base reference image, which if you think about it as a 2D convolution, that's your kernel. And then in order to speed up that process, I also have a downsized versions of these also cached in memory, where when you do a correlation, what you actually do is you do you basically take the downsized versions of the image and your kernel. Current downsize factor is by 4, so basically you're doing a 4x4 subsample, and then you do your 2D convolution of that kernel over that image to get your response function, which tells you where the kernel actually is in your image. And then once you get the results from that downsized operation, then you can crop on the main image to limit the space of your full resolution search. So it's basically like a coarse image search and then a more fine image search. And then on top of that, once you have those coordinates, you can crop around the center core based on that coordinate, and like do a centroid to find the absolutely like most accurate centroid position for this entire image on the bigger image. I think it's been a while since I did a lot of this. From a high level, it's just coarse 2D convolution on a downsized image, and then a fine 2D convolution on the full resolution, and then you do your centroid to find the location, and that's how we do like our image correlation.
And that is happening in the CPU?
That is
on
all
the
happening
NCFI?
in the CPU. Also, I'll note that one of the reasons why we didn't do any of this in the GPU is because adding the GPU's, the CUDA schedule on the GPU is so optimized and very delicately put together to match our computational cycle timing requirements, that any additional nodes that we put on there will potentially screw that up. So I talked to Patrick, and he was very much against like putting anything like this in there. Because we were able to do like stuff like the coarse search, and then your fine search, and then your centroid, that is actually significantly faster than if you were to just do a full resolution 2D convolution of your reference image against the entire full image. And we cut the runtime down on that so much that we didn't really need the GPU anymore in order to meet our alignment timing requirements on our previous prototypes. So, again, no need for GPU use at the moment, but if there's any other more complex and operations that we need to do on the images, it could be worth potentially looking at introducing that to the GPU again, especially if we have any like GPU upgrades planned in the future, which I'm sure we do. But yeah, that is basically image processing. Like
So in the NCF5, you call this at some moment when you send a specific function to call it and to connect or whatever in order to start running it, or does it start running it automatically when you turn on the NCF5? I assume you need to call a function, right? Like
yes.
connect,
yes.
start.
Yes. So that's the next part, which is kind of how this is integrated into our start routine. So the way that I'll just talk in terms of our free space connector M designs, which is again what we've used for the CIP goals last year, because a lot of the software changes needed for this guy hasn't been made. But basically for that design, what we did was for Contour, you would call the normal startup procedure is Contour init, so that is on basically program launch, and if the Izifo app has been configured right, then yes, that's basically on power up. And then once Contour init runs, you run Contour setup, and then once you run Contour setup, you run Contour start. So setup basically like sets up, like for example, our
calibration files.
So the cal file is actually a separate step, but like there's a lot of other things we need to do, like for example, setting up the laser and setting the acquisition mode,
okay,
and like allocating memories and for our GPU and also CPU and stuff like that. That all happens in setup. And then also another thing specific to the free space connector application is that's also where you establish connection to our FMC or FSMC. So there's an additional option that gets put into all of our free space connector setup arguments, which is FMC, which tells the MCFI like, oh, go and look for an active FMC or FSMC that's connected, and initialize it, right? And then once setup is complete, then you actually run start, and start starts the acquisition cycle. And
very much.
starts all that. And then during start, so in the context of when our MCFI is actually in the ION system, setup basically runs like as you set up the bigger system, and there's no catheter attached yet. But start only runs once you have a catheter attached. So basically the action of attaching a catheter triggers start and starts all the shape processing so that you can do like your system checks later. Our alignment procedure, because it also relies on, well, for example, our image in order to do closed loop feedback, but also we need acquisition to start to also be able to first transfer this image data, but also get our actual like shape signal so we can determine whether or not we're aligned and stuff like that, and also to do signal optimization. So during start you have your start acquisition, and then your free space connector alignment, set up an alignment, and then the rest of the finishing steps for start. So the target is by the end of start, your system is coupled and ready to be continuously used. That's why the alignment procedure is in start, like kind of in the middle of it. There have also been efforts to, like, because one of the big targets that we had before was to cut down on the time it takes to run that alignment. So like it was whatever start was originally going to take, like, let's just say like 6 seconds for MC5 start. We wanted to make sure that integrating the free space connectors alignment would only add 10 to 15 seconds to that alignment time. So there was an effort to, like, there's a lot of like FEMC setup work, and like, for example, things like homing the actuators and stuff like that. We made an effort to move a lot of that to the setup step at the beginning, where we don't really need a catheter attached, but we still need to run, like, for example, homing and stuff like that in order to initialize the free space connector. And that's how we were able to get it to like 10 to 15 seconds. It used, with all that added, it used to be like 25, but moving stuff to setup cut down on it like pretty significantly. Any questions at the moment? Does that make sense?
Yeah. I would like to see where, if you know where it specifically is, in which files are those calls.
So
start.
Yeah. So
setup, contour.
So the
underscore setup.
Yeah. So the and the software team can give you a lot more context on this, because setup and start is not a free space connector only thing. The only free space connector only thing is
but it should be in that file. Contour start.
It is it's free space start, free space connector align. Free space startup, and then free space align.
Nice.
So you can trace this function down and see all the routines and functions that this calls.
Perfect.
But yeah, and I've also tried to make my best effort to keep all the free space connector like files and utils and functions in their own files. Some of the more key ones are this free space setup this file, the CPP, which does a lot of the like actual setup steps, like for example the homing, reading our free space connectors calibration files, which I'll get into a little more later, and then like initializing our motor drivers, setting up the right like FMC registers and stuff like that. And then the other key piece is this free space connector align, which is the bulk of the actual alignment procedure. So using our image to align, to do our autofocusing, and then doing our X and Y align with the image, and then doing signal optimization in X and Y as well. All that is in here. And there is this, I also have a range of free space connector CAPIs that are all here in this header file. It's implemented with the same macro structure as the rest of our CAPIs. And then there is also, for every CAPI that's in here, there's a mirrored LabVIEW client function in free space connector and then CAPI in here. So every single one of them
can you
has.
hold it?
Yeah. So every single one of these functions.
I mean, can you move this folder to
Yeah.
this? So.
So this is in the LabVIEW repo. So this is in the LabVIEW repo for the free space connector, which is on SVN, and
So you
go
have
into LabVIEW.
you
free
have the
space
wrappers
connector.
now.
Yeah, all of this is so. I've tried to make sure that all of the free space connector related things are in this free space connector folder, and then if you go into CAPI, there's a function for each of these CAPI functions. And
the CAPI functions are just related with the server, right? And they call the internal.
no,
functions,
it's
right?
related with everything. So everything that you want to do with the free space connector goes through a CAPI, basically.
Okay.
Yeah. So while we have like, you know, as we've mentioned, we have the align and start procedure in the start routine, but like just day-to-day work when we're not like, you know, running the system as if it's in product, for the most part you're going to be using CAPI functions to call everything. Like for example, this start free space alignment function also has a so there are some bigger steps, like for example the focus Z and stuff like that, and align X and Y. All of that have their own corresponding CAPI functions as well. So like for example, if you just want to,
Can you open just one, just to see
yeah,
what you have internally?
it's just this,
Okay.
because all the logic.
Exactly.
Yeah, so you're basically calling this our MC5 client, which is again our DLL.
Nice.
So all you're doing is
That's
telling
it.
it the function name and then
Exactly.
the arguments, and then it'll run all this like actual logic of the workflow is in our embedded server. So
Perfect.
so yeah,
Nice.
so I guess like generally generally the way that, you know, you separate the logic is like, if it's something that eventually has to go into the deployed version of our free space connector, like production free space connector code, then it's worth implementing on the server side. But if it's not, then it might be easier to implement it on the client side,
Okay.
so that you can, so that you don't introduce like additional clutter to our server code, and then also it's easier to manage on the client side. One other thing that I had to add for the free space connector was a lot more like FemC.
Exactly. I was going to ask you about the fancy.
Right. Yeah. So
Like,
because
there's another layer that communicates with the fancy world, right?
yeah. So outside of the free space connector with just regular Contour 4, a lot of these FemC functions, like for example, generation of the curves and like converting like target move distances into like actual motor counts for our FemC based off of like motor configurations. All of that was in LabVIEW. Like all of that was on the client side, but because moving the motors is a key part of actually using a free space connector, I've had to translate a lot of that and move a lot of that into our embedded code base. And there are like CAPI functions exposed for that, but this is a very, very minimal implementation of basically all the logic that we have on our LabVIEW FemC library. Like I only support stepper motors here. I only support a very specific set of motor drivers, and the only curve type that I support here is like trapezoidal. So there's a lot of other fancy like motor control setups for it in or like EFTs and stuff like that I don't use here.
Those are in LabVIEW, but not in here.
Yes. Let me see if there's anything else on. Oh right. Let me also go over kind of like the different calibration files that get sent to that are associated with each free space connector. Currently, the way that these cal files actually live for a free space connector is in the form of like a text file or a TOML file, and then basically we have a very custom like set of functions in LabVIEW and Python that write all these into named values in the MC5. So currently the implementation is that like upon that this text file basically gets flattened into a binary and gets stored on the MC5's disk, and then upon every time on startup you would read whatever is on the disk as the free space connector cal file, and then read all of these values into the named value manager, which is a key part of Contour. And then, but however, the target design for this, because if the way that we have it right now is the cal file actually follows the MC5 instead of follows the free space connector. But we really want it to just follow the free space connector. So either on our imaging board or our motor board, there would be a piece of flash that we can use. And the idea, the target in the future, is that these calibration files would basically just get stored on those boards instead, and then you would read flash and write to flash as you would any other board. So then you don't have that like file on the MC5's disk that follows the MC5 around. There's one of these generated basically for each and every free space connector. A lot of these are outdated and obsolete values, The key ones here, a lot of these are like thresholds and like parameters for your search algorithms and stuff like that. But the key ones here are actually the most important and often the only ones that you really have to adjust. Is this target image position, which is basically the reference image position, which means that like given a free space connector and assuming that it's calibrated and hasn't moved or it hasn't changed since that calibration, if you move this image of your in focus end face image to this very specific image location, then you would basically be very, very close to coupling, if not already coupled. And that's the main heuristic that allows us to actually do an alignment in such a short time is this guy.
And how do you get the reference image? Like
the reference image is so like what we tried to do yesterday, or also what we're trying to do right now when we're setting up one of these systems. That is a key part of getting this value. So assuming that let's assume that we got coupling yesterday, right? What would happen is that you would basically have an image here, and then an image position here that corresponds to your ideal coupling.
I see.
And then what you would do is basically assuming that you don't have to change the focus of the camera anymore, because like moving the camera also moves it in X and Y. But as long as the system and the actuator is in focus, or like the system and the actuator doesn't change, you'll still get shape. So it doesn't matter if you move the image around, as long as you update this value that goes with it. You would run one of these correlate functions, the correlate CAPI, and it'll give you like this output value where like, oh, here's where the image should be when you get coupling, and then you just.
On the screen so that video is recorded.
Oh yeah. So basically, the idea for that reference image, and this concept is outlined pretty well in that invention disclosure that we did that we wrote for the alignment routine. But the idea is that in manufacturing, you can afford to take the time to do these brute force searches, like the one that we did yesterday, right? And you're basically disregarding the image, like you don't really care where the image is, but you just scan through the actuator's entire range of motion until you find your position of the actuator with the ideal coupling, right? And then you fix your camera so that, and the camera will stay relatively fixed relative to the coordinate system of this entire free space connector, and especially the hex pack, the capital side optical components. So, but you're looking at basically the instrument side.
You need to change or fix the camera. You're saying again? Like,
Yeah. So when you do your brute force and you're looking for your gratings, you don't really care where the image is at the moment.
Mm-hmm.
Like during calibration, you don't care where it is.
Mm-hmm.
You just care that you get signal.
Uh-huh.
And so that gives you a position for that actuator, for that sensor that you have attached during the calibration procedure.
Mm-hmm.
It's basically telling you like, hey, in this actuator position for this sensor, we're coupled.
Okay.
And then we introduce the image, the camera to our system, and then we fix it. So it does from here on out, it doesn't move relative to the rest of the system. And then you use the camera to look at where the image of the end face of the instrument is, and that gives you the pixel coordinate. And because the camera is fixed relative to the system, in the future, any time that you attach a different sensor, which may slightly vary in X and Y and Z compared to the golden sensor that you use during calibration, but since you have that reference image position, as long as you drive it to the same reference position, you'll get coupling. Like that is because of the fact that the image sensor is fixed relative to the rest of the system, regardless of what instrument that you put on it. Does that make sense? So the idea during calibration is that, like, hey, once I put a golden sensor on it and I get coupling, and I move the actuator around until I find you put this sensor on and you move the actuator around until you get coupling, and then you take this reference image position, and then that is your heuristic for the rest of this connector's life, until you like move the camera. If you loosen the camera and you shift it any other way, that calibration is no longer valid, because that calibration is tied to basically the information that you encode is actually the spatial relation between the camera's current coordinates and the rest of the system.
So the image sensor is totally different from the camera.
No, the image sensor is the camera.
Because you mentioned that you have a golden one, and then you have another one.
Oh yeah, so there's right. So I've been using image sensor and camera interchangeably, but this is our shape sensor. This is our actual instrument sensor. So like I guess there's two sensors in that regard.
Okay.
Does that make sense at all? Is there anything that's confusing at the moment? Because
just about the terminologies that you were using,
sure,
about the
course.
image sensor and the camera is like it's just an image sensor, right? Not necessarily a camera, but it's what you were saying, right? It's not like a camera at all, right? It's just like a sensor that collects the light and that's it.
Yeah,
right?
yeah. So yeah, we can just call it an image sensor from here on.
And you use one, and it's gonna be that same sensor that you're gonna be using later, because you were calling
Yes,
one
yes.
the golden sensor. But when you were saying golden sensor, you were saying about the.
I'm saying about this guy.
Okay,
This
okay.
guy,
I see.
yeah.
I see what you're saying.
So yeah, you have. So basically, again, like
I see.
the whole point of the free space connector is that when you're making these high volume shape sensor parts, that there's a distribution, right? Like if you think about it in terms of its tolerance in 3 dimensions, like manufacturing tolerances, like this could be in microns, but even microns is a huge deal for our very specific application. You'll get like a Gaussian. You can assume that it's like, let's just say like it's a Gaussian across each dimension. And then we actually can have a golden sensor in manufacturing that we use that we think is the most representative of all the sensors that we're ever going to produce, right? It's right smack in the middle of all the Gaussian curves. And then, so that puts us as close to, like, as representative of our population as possible. And that's the sensor that we'll use to get our reference image. And then which, again, like, because the image sensor is fixed relative to the other system, every time you put a different shape sensor on it, as long as you drive this image to the reference,
you need to recalibrate.
No. As long as once you put a different shape sensor on it, so like a different catheter onto it, as long as you drive it to that predetermined calibrated reference image position, it's more or less very close.
Okay.
And the reason why I say it's more or less very close is because there are still minor like deviations in terms of like thermal changes or like things like that, or like angles and stuff like that
Sure.
You know, like make this reference or calibrated position slightly off. So that's why you still need to do a localized signal search. But like you might not get perfect coupling, but you know you're really, really close.
I see.
You're definitely very, very close to it. So then you can actually afford to do a more brute force approach to like, you know, like actually find optimal color.
And how do you populate the values of the calibration file?
So, like I mentioned, a lot of these are obsolete values.
Like they will be fixed for every new.
So some of these are just
Free
not
space
straight up
connector.
not used at all. Like for example, these guys, the Q1 hard stop and Q1 home moves, these are in radians, and it's very specific to that design, which is no longer relevant. So I'm sure that as you develop a different setup for the Delta robot, that you'd actually have also different calibration values. But this is just generally the way that we've been storing these calibration values.
I was going to ask you also that all these scripts that you have that are already in the MCF5 boards works with previous versions, like the current and latest.
No, like a lot of it doesn't. So you will need to either revert to previous versions or
On the Bitbucket repository.
I think I think at this point it's extremely unreasonable to like
To go back.
run any like older versions, especially since the control setup is so different. And also, like for example, our boards, like we've gone through like maybe 3 iterations of the boards, and unless there's an emergency shortage of like boards and we need to spin up some fixtures fast, there's really no reason to go back to older boards and older like registration mappings and stuff like that. So yeah, all of so the alignment again, like I'll mention this again, but the alignment routine is all implemented in between the setup and align files.
Are there any other values in the calibration file that we need to look at and change it manually, or any?
Yeah. So for the most part, this is it.
And they are manually. We need to change it manually.
Yes. And as I've mentioned, the way that this is currently loaded into Contour is because it's stored on disk. So there is actually there's a tab here.
Or maybe you can move it through this window.
Right. There's a tab here currently that like, hey, you can upload your free space connector params or cal files or whatnot. The other thing that is a part of the calibration files is the reference image. And so like when we were talking about the image correlation where you're trying to find where the end face actually is, we're doing a 2D convolution, and that requires a kernel. The kernel is this guy. This is the reference image.
Okay.
And previously, a lot of the times what we did was we just took, like a real image and then cropped around it, manually obtained an image by cropping around what we find is the end face. And we can actually test that out real quick. But what we previously did was just this, and then you would just select a location, generate a reference, and then you'd save it as a .ref binary.
Okay.
And then you can upload that file to the MCFI as something that stores again on disk. But one thing that we found is that you actually don't need to use a real image for it. You can actually generate a synthetic image of the ideal end face image, and it works just as fine. One thing to note is that the size of the end face varies depending on your magnification, the magnification of the optical system that we use. So like right now,
So there was a different type of image, right? Is it in different locations or all?
no,
were
just the
acquired?
size, just the magnification of it. So like right now, this guy's like what, 200 pixels wide. If you change the focal distances or distances of any of these lenses,
It will.
it will change.
It will
This
change.
magnification will change, which is why we have this like setup to obtain and update your reference image very easily, and it's not hard coded into the the embedded code
Mhm.
is because we change our focuses and magnifications all the time. So that's just something to be aware of. A couple other things. Sorry, go ahead.
And you need to have a reference image also because for every new sensing sensor that you're gonna be putting, and also for the active alignment, right? Are you using the reference image for the active alignment?
No.
Oh?
So for
You just
well,
follow
what do you
the signal.
mean by active alignment? Because like I think this is a term that gets muddled a little bit. But we have initial alignment,
Oh,
and
just
then
to,
we have active alignment. Initial alignment is when we just put a catheter on, we don't have shape yet, and then we have
Exactly.
to get shape.
exactly.
And then there's the active alignment part, which
It's just to get rid of the thermal drift. and-
yes, so like
mhm.
you already have coupling at the beginning.
Mhm.
You have to maintain it for
Mhm.
however long
Mhm.
that the system's running.
Mhm.
So those two are very different concepts
Mhm.
and deploy very different strategies
Mhm.
because they're fundamentally different problems.
Mhm.
But for the so are you talking about the second part?
Yeah, the second one. Yeah.
So, so for the, so I don't think that well, this could change. There's a lot of that second part that still hasn't been implemented.
Mhm.
But for correcting a thermal drift, we don't use the image at all
Okay.
because the camera is also has some thermal drift introduced to it.
Mm.
So it is that reference is no longer the most reliable source of truth, but rather the most reliable source of truth is signal itself. And the way we actually track it is like doing your localized signal search or your gradient descent. So you scan around a really small circle. You never really like lose shape, but it's enough for you to actually see variations in the grading intensity or the grading amplitude so that you can determine like, oh, I should shift a little bit this way so that I'm following the peak of where that grading is, right? That doesn't use the image or image correlation at all because we're not relying on the image. However, we do rely on the image correlation if you want to update your reference position.
Okay.
So that's something that we can do. The second part, which is more like the core tracking, like for example, if there's a really fast move, like this pole wire yanked on the catheter and it moves like so all of a sudden to that's a really, really fast move. And because all of those, this is all written out in the invention disclosure, but if this thing moves really quickly and it doesn't impart any forces or deflects the camera at all relative to the system, then you can actually use the camera to like track the position and then like, oh, well, I'll just move that. But because that's such a fast move, that this is actually something that's done at the FPGA level, and Joao's handling a lot of that. But the problem is you definitely do not want to do anything remotely close to like 2D convolutions on the FPGA. It's just like summation at the most integration and stuff like that. Very simple operations on like just the center core. So that step also doesn't use image correlation.
Okay. Sounds good.
Yeah. Does that generally make sense? You know, there's a lot.
Yeah. Yeah, it's fine. You know.
Okay. Two more other things that I'll mention in terms of like the cal files that get put on the system.
But there are no other parameters that are related with the motors that are used in that specific free space connector or build that you have for the free space connector that you need to put in the cal file. There is nothing like the Q1, Q2, Q3.
So that's what I'm going to do. That's what I was going to talk about next.
Okay, perfect.
Yeah, which is again, all this stuff is built very specifically for that unit. So a lot of it will have to change for the Delta. But the way that we did the 5-bar kinematics, so like robot kinematics or at least modeling the kinematics in this case, the problem that we're trying to solve is, say you have, like, let's just say a scenario where you have your reference image, right? You have your reference image position, your target position for where you want your image to be. And then you have a starting position of like, oh, you just put this new catheter on, and then now this image shows up in a different place, and there's this delta, right? What motor moves do you actually input to your system in order to move that to your target image? And that's what the kinematics model tells you. And the way that the 5-bar works is that because the 5 bars kinematics and also the deltas is very non-linear, so you can't just like, oh, let me just calculate the delta between these two.
Exactly.
Because it's also dependent on where in this entire range of motion these 2 points are. So you can use your image to estimate the general region of where your starting position and where your target position is in the bigger like actuator range of motion. And then you can then calculate based off the delta and basically like what delta Q you would have to input for your motors in order to achieve that amount of displacement at that very specific region in the actuator. It's a pretty hacky way. I don't think it's the most conventional closed loop solution method, but it works, and it works pretty well. Also because we don't have absolute encoders and we don't know exactly where things are all the time.
On the motors, you cannot move them absolutely, right? It's just relative movements that you do every time.
It's all just relative movements. It's all relative movements. So,
and when you are homing at the beginning, when initializing the FMC, do you move into a specific direction the motors in order to hit something and push something, and then
yes,
you have your reference? Okay.
Yes, and that's dependent on the design. So depending on what you're working with, there's a set direction where the hard stops are located. So that's just something that, like, you know, Graham will probably tell you, like, oh, I want, if you have to home it against hard stops, go this way or that way or whatever. And we don't actually calculate any of the kinematics on the embedded code. Instead, we have a series of lookup tables that are generated outside using MATLAB scripts, and this is all on Confluence as well as to how those are generated. But we've also done, and those lookup tables are all like ideal. Like that's based off of the ideal model of what the 5-bar is supposed to, how the 5-bar is supposed to work. We also did a good amount of testing, which is what you saw with like the flexure tracking,
the Q1,
like the reflective
Q2 tables,
that stuff. We did a good amount of testing there to make sure that the flexure actually behaved close enough to the ideal model so that we can actually use the ideal model as a kinematics model, and it was pretty, like, it was working just fine, so we used that.
Who defines the kinematic models? Like, I mean, are you in charge of building the kinematic models?
Yes. So yes, but that is also, I think that's a relatively trivial task because, like, all the, like, for example, for the 5-bar, all the joint lengths are already defined. Like, that's just like mechanical design. They'll tell you what all the joint lengths are, and basically you just have to plug it into a MATLAB script and it'll figure it out for you. But you do need to, again, like, since we don't want to do any of the kinematics calculations on our MC5, do it via lookup tables. And that's been working just fine. But I will say, for the delta, it's probably going to have to change a lot. So, just because, well, first of all, I've also written this out in kind of like the open items page that I'm putting together right now. But the delta, we still need to figure out whether or not whether or not like a generic kinematics model, kind of like these, would work across different units of our delta actuator. Because there's enough build variability in these where the kinematics behavior of each of these units are slightly different. Like for example, Graham was talking about where like as he's assembling it, some of these guys will just like rotate. Mm-hmm. It's not supposed to, but it will just rotate because of slap or whatever in the system. And then once it rotates and then you start moving it as if it's like a regular delta robot, it'll deviate a good amount. So there's some investigation that needs to go into whether or not we can even generate one of these like generic models, like in the form of a lookup table that applies to all of the delta robot units, or do we need to have a very specific calibration station basically for each individual delta robot to obtain its own lookup tables as a cal file for this very specific unit. That's a whole different discussion. I have no idea what the answer is to that. But like conceptually, we were able to like control this delta as if it's a 5-bar, like, you know, just given a start position and you have a target end position, you can actually move it to that. Like that's been achieved. It's possible. But I'm just saying, like, it's probably going to change a lot for the
Sure.
delta. And
Also, this lookup table, are you loading it into the MCFI?
yes, it's all on the MC5's disk.
In the CPU, right?
Yes, the lookups are done there. And a lot of these functions, like for example, a lot of these functions that are currently written in the embedded code base are in terms of like the 5-bar. So it makes assumptions that, like, for example, the Q1 is a rotational joint, Q2 is a rotational joint, and then Q3 is a linear joint. So right now, the way that I've been controlling the delta is I have this like hacky conversion on top of it to like convert the rotational linear joint values into rotational joint values as if it's like a 5-bar. So I'm controlling the delta. Currently, I'm controlling the delta as if it's a 5-bar, just with some weird conversions in between. But for best practices and less confusion, I think that should be corrected very soon.
Sure.
As you can,
Good
like,
to know
like for
that
example,
you have been doing that.
yeah, for example, here is here's the actual LabVIEW VI for moving the delta. Like inputs are move this leg by that many microns, but it's actually doing some weird like motor calculations to actually convert it into a move 5-bar command. So just for like clarification and like making sure that no confusion there, I think that should be
How do
fixed
you know
relatively
those
soon.
values?
Those values are based off of like our gearbox ratios that we use for our motors and like the pitch and stuff like that. And you know, our motor setting step sizes and stuff like that. So it's I think it's best to just like rewrite all of that because there's a lot of entangled things there.
Sure.
That's in terms of the motors. The last thing is this FSys config file. So we've talked about previously how like we can actually change the size of the ROI of our images. It doesn't necessarily have to be 1,000. It's just that we set it to 1,000 because it is convenient to use, and then we're getting data from it at like 20 FPS, right? That is configurable. and is part of this configuration. So what this file actually has is basically a series of register values to write to this sensor here to tell it like, hey, I want our image stream to be configured like this. The reason why we can do this, well, we can do this with any unit, but there's a lot of register values to be written, mostly because the image sensors that we currently have from the third-party vendor are engineering units. So a lot of these register values are not programmed in yet, but eventually when we graduate to a production series of sensors, a lot of those we basically can tell them like, hey, program this sensor like this and with these register values. So we eventually will no longer have to do a lot of that, but there are still a couple of registers that need to be written for that. Joao has been doing a lot of that and handling the programming and how to actually set up one of these, so he can provide more information on that. But just to mention again, like, this text file is basically also saved to MCFI disk and is loaded on startup or on setup to actually start our image stream. And all four of these, so your FSys config, your lookup tables, even though we're not using the fiber anymore, the reference image, and also the cal file, all of these have to be present in the MCFI disk. Otherwise, it will throw an error as it is right now.
Okay.
Yeah.
Also, all the .bin files that I was asking you, like, what were the meaning of those
So
files and
So
and the V10,
yes. So V10 is a contour event. First of all, do you guys have a time cutoff? You feel like the bind time?
Oh yeah, yes. If we have time to.
Oh yeah, okay. So you
Yeah.
don't have a hard cutoff for.
No.
Okay. So the V10 are contour event logs. So that's not a part of just Free Space Connector. That's something that we do on the regular with
sorry,
contour
you were
anyway.
talking about a little break, or
Oh no, I just was wondering if you guys needed
okay,
to leave
okay,
and if
I
I
see.
should speed it up.
I see.
But, the V10s are generated through contour event logging, and right now, an event log is collected every time you complete start. And this is outside of what Free Space Connector is doing.
Okay.
And it's basically just a snapshot of the system. So like shape and the quality of that, and like a snippet of our DSP data and stuff like that in our event log. So that's basically just like when we collected that for the CIP testing as like data for how well our final state after the alignment is. The aligned data bin file that I've also been collected is a kind of like a recording of all the decisions that have been made and all the data that's been used for processing during the alignment procedure. So you can see more of that. It's a pretty open and sort of generic like data structure, but a lot of the data that's being collected here are basically screenshots of the images during different stages of the alignment. And then your autofocus curves, so like as you move the motor, what does the focus curve look like? And then like your closed loop, like when you're moving the image from one XY position to the next XY position, what your trajectory was. It's all stuff like that. And then also eventually when you do your signal-based alignment, your brute force search, how many steps you took, what were the values at each step and stuff like that. So it's all like intermediary values. It's mostly there for like debugging purposes. So like if there's a alignment procedure that went wrong and you want to see what happened underneath the hood,
And how can I read them?
there are
Do you have?
yeah there are VIs for that. Let's just say yeah. So this guy, because we didn't run an alignment procedure at all, but this is a monster of a parsing VI for reading the values that are collected here. Right now, just the values themselves, I think, don't mean much until you actually look into the source code for what each of these are. And I'll just, like, for example, if we go into a line, and then we take a look at, let's just say align X and Y, the XY alignment. Basically what this align data is a variable that's stored at the contour singleton. So like any alignment function here can access it, but you can add a data point for it, which is while you're doing your loop for collecting moving closed loop from one image location to the next. You'll add, wait, where is it? Oh, right there it is. Right. Sorry, I was looking at the wrong function. But this is the closed loop actuator move to target image position function. And at every step here, you can basically, well, it's commented out right now, but you can add to this alignment data structure your intermediary values. And I've designed this very specifically so that you can add any sort of like value name, and then it will just append it onto like a 1D array. So you do also kind of need to know what you're adding in order to actually parse it on the other end. So in each subroutine, you would call you would get the very specific like variable name that you just added, and then it'll give you the array. Let me see if I can. Does that make sense? So that bin file is basically just
Information.
one big lookup table or one big dictionary for 1D arrays, and then the alignment data or the alignment routine just populates that with intermediary values that are important for debugging, like the focus curves and stuff like that. So yeah, it's again like it's not very well structured, and I purpose and
Just to troubleshoot the system.
yeah, I made it a very open kind of data structure because so many things change, and like for different debug purposes, you might want to add different values.
And you used to store them as a bin files only, right? And you used to use the unwrapping BI that you were showing us
Yeah.
to see the values of
Mhm.
specific ones.
Yeah. So you can read from a binary file, but there's also a copy function that basically just retrieves the current aligned data or the current alignment routines data as it is in memory on the MCFI. So like if you just completed an alignment, you can call this to collect and capture that data. If that makes sense.
Do you think we will be using it
I think so. It's you'll definitely need some sort of data generation and like data collection setup. It probably won't be what I implemented because later down the line you'll know exactly what you want to collect and how exactly that data should be structured. But I didn't really know that while I was designing this. I just needed to collect some data, and I needed to add fields dynamically. Which is why I have this like setup for it, but it can definitely be refined and be more of a strict type def eventually at some point. Yeah, so that's what that binary file is.
Okay.
It's as the name suggests. It's data on the alignment.
Okay, perfect.
Let me see on my email agenda.
All this is getting targeted to Picargo, is that right?
Yes, that's the plan right now.
I thought they were updating the Argo line upstairs to Contour 5, right? So this will soon-ish be converted to Contour 5, right?
Likely, yes. I haven't heard anything from anyone about that, but it seems like it's likely.
The Contour 5 ambassador.
Oh, are you?
Yes. I updated the production tools to Contour 5.
Honestly, because there's so many new things here, like all the cappies and all the new data structures and type defs, it is a very, very significant project, it seems like.
Yep.
Plus, again, like I mentioned, a lot of it has to be rewritten for this anyway. So yeah. One last thing that I'll go over. So we've kind of looked at the LabVIEW client functions. I'll mention a couple more that could be relevant. But the main utility that we've been seeing here is this guy, this free space diagnostic one. And there's this other util which we've been using for looking at the image stream, this guy. That's just underscore image stream. And that is here. That is here. There's a bunch of other stuff in here that are all kind of like, some of it's one-off, some of it's sub-VIs, and some of it are just like one-time tests. There are also a number of VIs that are built specifically for the Delta in more recent times. They're all in this Delta folder. The cappies are cappies, but then also this M1V1 alignment has. This is basically an old version of the alignment routine where everything is on the LabVIEW side. So instead of coding all the high-level logic on the MC5's embedded code, like what we've seen with like all of this, like everything in FSOC align or stuff like that. This is all relatively high-level stuff that's in that file. But this is basically all that, but implemented in LabVIEW. And that was the first ever prototype of the alignment routine for that design. So like, if it helps to reference this guy, then that could be useful reference. Other than that, I'll also really quickly go over the contents of the Python client library. which I'll make this quick. But again, this is again on Bitbucket. But basically, this Python library is just trying to like provide you enough of interface so that you can call CAPIs, use our client MC5 client DLL to call CAPIs, get data back, and then also display it on GUIs and stuff like that. There's a Py project with a TOML file with all the dependencies here. This README is pretty comprehensive. This pretty much tells you everything about the repo, so definitely use this as a reference, but there are a couple things that I will mention. This MC5 module is everything that's not necessarily strictly related to the FreeSpace connector, but things like get results. So when you want to get like your time domain data or like your FEMC frames and stuff like that, you would use this. There is a contour module, mostly for things like, you know, contour start and stop and like set cal and these like high level control functions. And then everything FreeSpace connector related is in this FreeSpace connector module. And I have some applications of some GUIs for this. The way that I've set it up is I wanted as many GUI components as like reusable modules as possible. So a lot of these apps will reuse modules as they're implemented in the GUI folder. So these are all like GUI components here. And then I have scripts that you can run just from command line. These are like really quick functions. Like for example, if you just want to home the delta, like there's a script specifically for that. One other thing that I'll mention is that I also have a auto testing module, which basically means that I wanted to build a execution pipeline where you can run an automated test. Like for example, if you have some tests that you want to run on the delta, like testing the backlash and stuff like that, that when you run the test, it will also automatically run an analysis script and then automatically generate an output report. And I've implemented this so that it's all under this like underscore FreeSpace connector testing, and each of these folders, each of these modules is basically a test. And what it has is it has a collection script. So this is basically what you're actually doing while you're collecting the data of the script. Like for example, for this backlash test, you're actually telling it like, hey, move a single leg by this much, and then, you know, collect your data in a CSV. And then this attached like Jupyter Notebook is how you actually generate the report, and that gets automatically called and then outputs a report in an HTML file that you can open up in a browser. But that gets outputted currently to this auto test reporting folder. Like for example, this is like each of these is a test that we have, and whenever you call a test, it will generate the data that you collect, the raw data, and then the analysis, which is again basically just an HTML rendered version of the Jupyter Notebook that is associated. So it was just like I was tired of like manually running these like Jupyter Notebooks for analysis, so I just built this. But it is a pretty, like, you don't have to use it, but I found it to be a pretty useful like quality of life thing. Especially like, for example, if you have to run an actuator test overnight, or like you have to go and leave to go to a meeting, but you still want to, deliver results to a person, you can just point them to this folder and tell them like, hey, just check every now and then to see if the tests are done, or just less hassle.
Nice. Mm-hmm.
But other than that, I think the READMEs are pretty comprehensive, and it should be more or less self-explanatory for how to run it and stuff.
And the CUDA code that you developed for putting it to add it in the GPU.
So the CUDA code doesn't. I haven't added much at all, other than
just like to know where it is located. Yeah.
So it's all. So all of our CUDA stuff is in Contour Math, and also in like Z4 CUDA and stuff like that. The other software guys will be able to tell you more about it, but
Like James, like
yeah, James is our CUDA guy, but the only series of things that I've had to add is dedicated memory for the image data in both the CPU and the GPU for DMA, and also this little step here, which is an additional computation node, which is just like retrieve image data. So it's just a DMA operation.
and also did you do something in the ODC and the ONC?
There's nothing done on the ONC side, but the ODC, we do need custom firmware for all the free space connector stuff, and that is all Joao.
Related with Joao.
Yeah. And he can point you at any point. He can point you to the most up-to-date ODC firmware version, and he can also tell you more on like how to actually deploy it in Flash or ODCs and stuff like that. So basically, every time you have to bring up a new MCFI for free space connector stuff, obviously like check out this version of the embedded source code, and then like build it. But also you need to make sure to update the ODC firmware as well to be the free space connector version.
Sounds good. Yeah, because this is the one in the Bitbucket repository, right?
Yes. That ODC, I don't know where right now. That ODC, the most recent image, that is just on shared drive. But I think the source code for it is also on Bitbucket.
All right. Thanks so much.
Yeah. Any like big questions at the moment? Some of the stuff that I talked about in terms of like, you might have to do this in the future and stuff. I have been trying to compile it in a separate Confluence document so that it doesn't get lost. But it's kind of a lot. It's this ecosystem of software tools and code and stuff like that has survived a number of systems upgrades and like changes in the design and all sorts of things. So some of it is a little scattered and like a little piecemeal and not exactly the most well integrated and consolidated, but it works.
Sounds
But yeah,
good.
I would say, like, if you have any questions about the alignment routine, Joel is probably the next best person for that in terms of like how the alignment actually works and why are we doing this step and things like that. Joel is pretty familiar with that.
And if we can set up something for tomorrow or later, I don't know if we have time. It's 12 already, but to run the process, the whole process.
I don't think we can at the moment.
Okay. Oh yeah, because of
we can't do that.
But there wasn't a previous build that you were using, like another build that before this is the build 4, right? There was a build 3.
I mean, so a lot of what we talked about in terms of
It's
automated
just the same
alignment,
thing.
it hasn't been implemented. It only works for that 5-bar design. So
Okay.
nothing in terms of the automated alignment has been implemented for this Delta relay. And that's a huge chunk of the software work that's going to come, is migrating all of this and making sure that it works at this guy.
I see.
Yeah. So we don't have an automated alignment procedure right now.
If I ask you to do the auto alignment procedure of the previous version, can you do it? Like, can you set it up on the? Can you use the MCF5 and, like, for example, to see it tomorrow how it works and?
We probably can. I guess my question is like, what do you want to see?
Like to see what's the expectation to happen at
Okay.
specific
Well, I mean,
moments.
we have
like,
we have.
I mean, it shouldn't necessarily be right now. I mean, it's
Yeah,
just
we
like,
have
We're not gonna continue to look at code right now. Can we
no,
stop this?
We just one.
Oh, maybe
second,
yeah.
one second.
Okay.
We have recordings of our alignment.
Oh yeah, I saw that too.
Yeah, so
you put it in the
so like
yeah, Confluence. Yeah.
look, like, see, this is our 5-bar. This is our autofocus routine, right? So like optimizing for the Z, and then you actually start moving the X and Y, and then it's a little harder to see. Oh, that's actually the homing procedure. But then you move to your target position, and then you can't really see right now, but it's probably doing like a localized signal search to get optimal signal, and then that's your alignment. But then if you see it on the, actually I should just show the synced version. But like,
I
yeah.
saw those videos. Yeah.
So you're doing your Z homing, and then you're doing a Z like autofocus routine, and then you're doing your X and Y home right now. But that looks very different for the 5-bar, and then you move it to some target position, and then you do like your localized signal search, and then you have signal.
Can you point on the BIs that you used to do that? Was it done on LabVIEW or Python?
This was all done as a part of our embedded code.
Okay.
Yeah, this is all.
Okay.
This is all what we were talking about earlier.
I see.
In terms of like all of this, and what was that? That
I
was
see.
Like,
I see.
that was 29 seconds. So again, this was with all of the homing routines, homing procedures, like doing
I
the
see.
Z, the big Z, and then the big X and Y for both of the
Got
motors.
it. Got it.
We moved, since this recording, we've moved a lot of that setup step to before we even have a catheter on, so that all we have to do when we attach a catheter is from here, which is like, oh, you attach a catheter, move it to the calibrated position here, and then once you're close, do your
In
signal
here, you
optimization.
use only the values of the calibrated position, or you use also the image reference.
It's both.
It's both, okay.
It's both. You need to use the reference image in order to even calculate where, like,
The reference image gets you close, and at that point, then you ignore the reference image and go based on the signal strength.
yes, yeah. So normally what would happen, again, like, this is like outside of a thermal chamber or like very extreme, like this is in ideal lab conditions. Usually when you put it at the reference image, you have like 90% of your grading strength that you need. And then you just have to like optimize a little bit. But there are some times where it like the gradings are either really weak or like it's slightly off, but it's generally still in that same region. So as you can see here, what the strategy that we currently use for the brute force search is a spiral. But that spiral, you can as a part of the config files for this, in here actually there are some parameters for configuring that. That spiral can go on for a very long time, but that's just something to tune, and it's a matter of like retries and like how long you want this to like go until you call it a failure and stuff like that. So,
And the focusing value, that value that you get for to match focus, is just a correlation between the reference image and the one that you are having at the moment.
so
that
the
you are,
focus value is completely different. The focus value is focus is basically how sharp your image is, right?
Okay. Yeah, exactly.
So what you're doing for the Brenner's gradient algorithm that I'm using for focus is you take any you take an entire 2D array. For every pixel, you're checking its the delta between it and its neighboring pixels, and then you're summing that up across an entire image, and that's your focus value.
I see.
So, and like, there wasn't a reason why this like works the best, but we experimented with a number of different algorithms, and that one just happens to be the one that works the best with the least noise and the most distinguishable and fittable curve.
Nice. Okay.
So, like, I think that is potentially something to like refine and potentially test more, especially now that we have, like, you can see right now, when you're doing your focus routine, you can visibly very clearly see like a pretty distinct like change in focus, but since our Z compensating ratio on this guy is a lot higher now, you need to move it a lot further in order to actually create any sort of distinguishable focus like change. So the actual like how much that actually changes and how well you can fit that on a curve is going to change.
Okay.
Yeah.
All right. I think that's all.
Yeah. Yeah. Sorry, I couldn't. I just think that setting that up would potentially take up to a whole day, if not longer. And I think I still have some documentation in terms of like future work that needs to be captured.